World Spaceflight News Special Report.
So let's dig into two of those challenges in particular. So the first one, this differential recession problem. Anywhere you have two different materials on an ablative system, they're going to recede and ablate at their own rate, right? So one of the worries we have is that these seams between the avcoat blocks will actually start to protrude or gap below the surrounding avcoat, causing local heating augmentation, right? If you stick something up into the flow, into the airflow during entry, it's going to cause local heating augmentation. If it does, it means you need more avcoat thickness behind your the thing that's augmenting the heating, which means your mass goes up, and you can kind of get into a little bit of a runaway thing with that. So one of the ways we look at this is through progressive arc jet testing here. So up on the upper top, you've got a simulation of the EM entry profile. It's actually a skipping entry, so you've got two spikes of heating that occur. And what we've done is we took 4 separate test articles. This is a Pathfinder. We took 4 separate test articles, all built exactly the same with this RTV seam in the middle. Run the first one through the first part of the trajectory, take it out, measure. Run the second one through a little bit more of the trajectory, take it out, measure, so on and so forth, to get a sense of how this interface might perform over the time of that trajectory. And so you can see we start to form a little bit of a fence there at the end. So this is the Pathfinder, first time we did this. We're just getting into this now, actually running currently in the arc jets with a whole series of different kind of profiles correlating to different kinds of trajectories, different places on the heat shield to get a sense of how this works. We're also, as an aside, implementing a system that'll let us measure that differential recession real-time in test instead of having to test different articles for different lengths of profile testing, because that can get quite expensive. Another challenge with this system, and it's kind of a challenge in general, it's more of a design philosophy thing, it's a risk posture kind of question. Likelihood and consequence of failure. So on any system, right, the consequence of a failure ought to, or should, dictate what your design policy is for that system. We talked a little bit about Apollo. They designed to average material properties, right? They showed that, well, it might crack, but if it does, it's okay. So what you might call that is, if you're talking about the failure of a crack, you have a fairly high likelihood that will happen, but the consequence is low, right? It might happen, but if it does, it's all right. What we found with the blocks is, as I've already mentioned, the likelihood of a failure happening, of a crack happening, is much lower. But if it does, it's a lot worse, or we expect it to be a lot worse, right? So you have a high consequence system, which must have a very, very, very low likelihood of that initial failure occurring. And you approach these two problems in very different ways, right? If you've got a bucket, a population, if you will, of strength data per se, like the plot in the upper right, and you lay it all out, let's say it's a nice, pretty Gaussian that comes right out of a textbook. You can design to the average of those properties, like Apollo did. And that's not very hard to do, right? You just look at your data, you take the average, you design to that, and if your system closes, you say, great, because I know that if it does fail, if I get some material on the vehicle that has less strength than that, I know it's not that big a deal. Well, it takes a lot of time and effort and sweat to show that it's not that big a deal, right? And you can think of that if you're familiar with a 5x5 risk chart, or some people call it a temperature chart. If you're going to move a risk from the right to the left, so decreasing what you think the consequence will be, that takes a lot of proof, right? You have to show that that's actually the case. So if you're going to kind of take the first road easily and allow something to happen, it takes a lot of work to go then and show that it's okay if it does, right? This is fracture tolerance or defect tolerance. It's a lot of work. If you flip it around the other way, where we are with the blocks, if either your design policy simply won't let you design to mean our average properties, which is the case on Orion, we use more, I wouldn't call them advanced, they're just different policies, designed to A basis, B basis properties. So we have to design to the 99th percentile low strength of our population, or 95th percentile low in the case of B. You're coming at the problem a different way. You're investing your time and money and sweat up front to show that your design closes to a very conservative estimate of what your strength is, right? So you say, I've got this body of data, population of data about strength of the ablator in this case. I'm only going to pretend that I'm going to get the 1 percentile worst case of all that data, and I got to make my design close to that. And that's where you spend your blood, sweat, and tears, as it were, right? That costs a lot to get the design that tight. because you're saying that I'm not willing to go down the path of showing that this failure is okay, because I don't think it is in the first place, and second, because I think it'll cost too much time, effort, and money. So in that case, if you want to think of it as a 5x5 again, you're spending your dollars, your time, to drop the likelihood down, or to show that the likelihood of your failure is way down here on the bottom. Now, I picked this chart for a reason, because where do those two triangles end up in terms of a qualitative risk? The same place, right? On this particular scoring chart. Different programs have different charts that score these differently. They could both be called high-risk systems, but they're very different in the way that they operate, right?